going to make it. Thank you so much for this invitation. It's really an honor to be here. You guys live in one of the cradles of human exploration, space exploration. There's maybe one other cradle of exploration, which maybe is in Lisbon, Portugal. I don't know. NASA is famous for astronauts. That's what you think of when you hear NASA, right? Astronauts and the International Space Station and the Space Shuttle. But NASA does more than just send humans out into space. We also explore through senses that are the instruments that we build. So my team might not be standing in the crow's nest of a ship sailing across the Atlantic, sighting new lands. We might not be sitting on the top of a rocket, a big tower of explosives, and launching ourselves out into space. Yet, we are, through our telescopes and our computers, searching literally for new worlds. And that's what I'm here to tell you about today. It's a project called Kepler, a NASA Discovery mission. And the title of this talk is Catching Shadows, Kepler's Search for New Worlds. Our Earth, this rock orbiting the sun, it's this rock suspended in a sunbeam, and as such, it is continuously casting a shadow out into space. We don't think of it, right? We're not aware of it. Well, maybe we are when we have a lunar eclipse, and we see that shadow that's being cast out into space sweep across the surface of the moon. Then we become aware of it. We are taking advantage of the fact that all planets like Earth that are orbiting stars are also casting shadows out into the galaxy, and then our job is to catch them. It is our hope that we will point a telescope to a large number of stars, and if we are patient enough, some of those shadows will sweep across the face of our telescope, and we'll perceive that through these senses that is our telescope as a momentary dimming of light. So that's how we're finding these new worlds, and I'll talk a little bit more about that in a second. Like all NASA missions, we have a very specific question that we want to answer. And that question is written here. What fraction of stars in our galaxy, in this Milky Way galaxy, how many of them, what percentage, what fraction, actually harbor potentially habitable Earth-sized planets? Worlds that we can stand on, worlds that maybe could host life. Potentially habitable. Okay? That's the question that we're trying to answer. But what do we mean by habitable? You know, if I asked you guys out there studying exobiology, what is required for life? What's required for life? Oxygen, okay. Yeah. Yes.
Living space.
Okay. Space. True. We get to craft open surprise. Go ahead, one more.
Solvent.
That's a really good idea. Now, the answer to the question, personally, if I were to answer the question, I would say pepperoni pizza, but that's just it's different. The answer you get is different depending on what creature on this planet you ask. Right? Some creatures don't require oxygen, for example. Right? But one thing we've noticed, no matter how extreme these creatures are on Earth, they do have something in common. And the thing that these creatures all have in common is that they are carbon-based. And carbon-based chemistry, the reactions like metabolism, all these life force reactions, require as the solvent, as this young gentleman pointed out, liquid water. So all of these creatures require liquid water. That seems to be a unifying ingredient. And so in searching for worlds that are potentially habitable, we're going to focus on this one example, and we're going to go chasing after the water. And so we came up with, not we, but scientists, astronomers came up with this idea of the habitable zone around a star. This is the Goldilocks zone. It is the distance from a star where it's not too cold, you're not too far away so that all the water's frozen, and you're not too close so that all the water boils away. You're in that just right distance where water can cool on the surface. Okay? And so in this diagram up here, it's not the blue shaded region, that's where it's too cold, and it's not the red shaded region, that's where it's too hot. It's that green shaded region. That's the just right Goldilocks zone. We call that the habitable zone. Okay? And you can see that it's different depending on what kind of star is in the middle. Right? It's like standing at a campfire and you want to warm your hands. It depends where you put your hands is going to depend on how brightly that campfire is burning. And stars are different sized campfires. Some of them are burning more brightly than others. Some of them are burning hotter than others. And that's going to change where that Goldilocks just right zone is. Now we can figure out whether or not a planet we discover is in this Goldilocks zone by measuring one thing. And that's the orbital period, how long it takes the planet to go 1/4 pass around its star. Because Johannes Kepler in the 1600s figured out that there is a relationship between how long it takes to go around once, the orbital period, and the distance from that central star, the distance from the campfire. So measuring the orbital period is going to tell us something about habitability. Okay, so how are we doing this? How are we finding these planets? Here's a cartoon of a star like our sun, and there's a tiny black disk that's passing right in front of it. That's called a transit. The planet is transiting in front, and on the bottom there's a green cartoon, a little line that's ticking along, measuring the brightness of the star. And when the planet passes in front of the star, the brightness increases. And that's a transit event. And this green little cartoon, we call that a light curve. These brightness measurements is a function of time. It's called a light curve. And we're looking for these periodic dimmings of light indicative of the presence of a planet. Now, for a star like our sun and a planet like Jupiter, that's what you see in this cartoon. That black disk is about the size of Jupiter. And Jupiter is going to diminish about 1% of the total light. So if you had 100 light bulbs and you just took away one, that's the change in brightness that you're measuring. But a planet like Earth is significantly smaller. This is what a planet like Earth looks like. You can barely see it, right? It's very tiny. A planet like Earth is going to cause a dimming of light that's 1 part per 10,000. You have 10,000 light bulbs and you take away just one. Or imagine the tallest hotel in downtown Houston. And every single room is occupied. Every single light is on in that hotel. And one occupant in that hotel lowers the blinds by 1 inch. That's the change in brightness that you're trying to measure from just lowering the blinds 1 inch. So this is what makes the science is very simple, the technique is very simple, but the technology, the instruments we have to build to achieve that precision is what makes this such an astonishing piece of equipment. So what you're seeing here is a picture of the actual camera that measures the light from all of these stars that we're observing. And so what you're seeing is a big slab of silicon, and the light falls on the silicon and then transforms that into a number that gets sent to our computers, and that's the brightness measurement. And so that slab of silicon is called a charged couple device, and it's exactly the same thing that you have in your cell phones, your digital cameras. Except the detector in your camera is about the size of your thumbnail. Okay? And this is a square foot of silicon. It's the largest camera that NASA's launched into space. And it's divided up into these squares. You see this square pattern. So actually there are 42 charged couple devices that are all mosaiced together. And so look at this pattern of squares, because you're going to see that at the end. We have a telescope, a mirror that collects light from stars and then sends that light to fall right on these detectors. And there's a bunch of electronics behind this slab of silicon that's going to measure those brightnesses. Okay, so projected onto the sky, here's that pattern of detectors. So the stars that fall underneath this footprint are the stars that we're targeting, the stars that we're staring at, and you can see it's very close to the plate of the Milky Way galaxy in the summer constellation of Cygnus, actually between Cygnus, the swan, this is the neck of the swan, and here's its wings, and here's Lyra with the bright star Vega, and just underneath the wing of Cygnus the swan that you can see in the summertime is this footprint that is Kepler's field of view. And there are 4.5 million stars in that about the size of my open hand against the sky. Okay? That might not seem like a lot, but a full moon is about the size of a pea held in a crystal, okay, or even smaller, half of a pea. So by astronomical standards, telescopes, this is a really big field of view. It catches very large number of stars. Of those stars, we cherry-picked the best 150,000 or so to observe, to monitor. The ones that we knew we could take measurements of accurately enough or precisely enough to detect, to be able to detect a planet as small as an Earth. The spacecraft was launched in March of 2009, so we're just about to finish our third year. We've taken about 7 billion brightness measurements of these 150,000 stars. And so I'm going to share with you our results. And the first thing I'll do is just give you kind of a bird's eye view of all the interesting things that we've seen that look like they are viable planets. And then I'm going to tell you about some of the research that we've done to follow up these planets and characterize them, to learn more about things like mass, for example, so that we can start to say something about composition, what these planets are made of, and to learn more about them. Okay, so the best way that I can give you this bird's eye view is to show you a scatter plot. And this scatter plot on the y-axis is the radius or the size of the planet relative to Earth. So if it's 1, it's exactly the Earth's size, and that's why I have a cartoon of Earth here. And this would be the size of Neptune, and this would be the size of Jupiter. And on the x-axis is orbital period, how long it takes the planet to go around Earth. And these white points that you see here were the transiting exoplanets. Exoplanets means planet orbiting another star outside of our solar system. These were the ones that were detected from ground-based observatories before Kepler launched, so right before that March 6, 2009 launch date, including some that are smaller that were discovered by a European space mission called Kepler. So looking at this diagram, what you notice is that most of the exoplanets that were discovered before Kepler were about the size of Jupiter, and they orbited with a period of about 3 or 4 days. That is, they went around their star once in just 3 or 4 days. It's very different than our own Earth. How long does it take our Earth to go around once? 365 days, exactly. Okay, so now let's look at what Kepler has done. And I'm going to show you 3 successive catalogs of our planet candidates, things that we see in the data that look like viable planets. And I'm going to show you them in succession, just 1, 2, 3. And then I'll back up and talk a little bit about them. So the first one was released in June of 2010, February 2011, and January next week. This will be released, the yellow points.
The new data set.
So let me back up again. Let me do that again. So here's what it looked like before. Here's our first catalog, June of 2010. Look how different they are.
Still bigger
In
than
our
that.
catalog, 75% or more were smaller than Neptune, not Jupiter sized at 4 days. They're different, right? And so right away we saw that it looks like small planets are going to be very common. Okay? And then adding February 2011, now we've got 1,235 planet candidates, and the trend is still the same. About 80% of those are smaller than Neptune. Okay? And then you can see going from the blue points to the red points, you don't have blue points down here. So the more data that we collect, the smaller the planet we can detect, and the longer the orbital period. You don't have any blue points out here either. Okay? And then next week, we'll put out our latest catalog, and now that number is up to 2,326. And again, you see more yellow points down here and out here. So as we collect more and more data, we're working down towards smaller planets at longer orbital periods. We're working down towards this bottom right-hand side of the diagram. And that's where we want to be, because that's where Earth is. That's where our Earth twin is going to reside, right? This is 365 days and 1 Earth radius. That's where Earth will be. That's where we're headed. Okay? Now what I'd like to do is change the x-axis. Instead of measure orbital period, what I'd like to do is use that orbital period to calculate how far away the planet is from the star, and then knowing how bright the central campfire of the star is, ask myself, okay, what is the temperature going to be at the surface of that planet? Okay, so I'm going to transform orbital period to that temperature. We call that an equilibrium temperature. Okay? So the points are the same, but we're changing the x-axis. And that's what it looks like. So here's temperature in degrees Kelvin. So these are the cooler things over here. All these are cooler, and these are really hot. At 2,500 degrees Kelvin, that's hot enough to melt iron. Okay, so those worlds are very scorching hot. But these are the ones that we're really curious about. Those are the ones that are in the Goldilocks zone. Those are the ones that are in the habitable zone. And you can see that they range from just about Earth-sized all the way up to twice Jupiter's size. Here's a little cartoon of Earth sitting there, and you can see that we've actually got a couple points that are just starting to kiss that Earth's location. So let me zoom in on this region right here. That's the points that are in that green region. Here's Earth. Here are the two that are just about Earth size. And we've got a range of candidates here, ranging in all different sizes. And you guys have seen the movie Avatar, right? The planet in Avatar, the movie Avatar, was not a planet like Earth or a star. It was a satellite or moon of a giant planet like Jupiter, right? So this idea that you could have a giant planet like Jupiter in the habitable zone that perhaps has a moon that could harbor liquid water on the surface is very enticing. We're very curious to know if those planets might have moons, and so we're looking at those very carefully as well. Okay. You remember that footprint that is Kepler's field of view on the sky, right? Here's what it looks like. Here's that same pattern of squares. And on the background is just a picture of the Milky Way galaxy. And here's the one of the wings of Cygnus swan. I've just blown it up a little bit. And the image that you see in the background on the squares, that's actually a picture that the Kepler Space Telescope took right after it launched of that region of the sky. And it's just kind of fuzzy. You can't really see the stars because there are so many. You have to zoom in really tightly to start to be able to make out individual stars. Remember, there are 4.5 million stars just in that one footprint. Stars that are in our own galaxy. Okay? So I've superimposed some yellow dots here, a couple blue ones, a couple pink ones, and I've got this number 61 in the bottom corner. These are the planets of that sample of 2,324, 26. These are the ones that we have done follow-up observations on from ground-based telescopes to start to characterize them. You know, let's confirm them. Let's measure something about them. Let's learn what these worlds are really like. So what I'd like to do now is just share with you some of those results so you can see that these are actually real places. So the first one, in fact, if I had to look back on the year 2011, I would say that it was a year of firsts, kind of milestones for our team in terms of these discoveries. We had a lot of firsts that were very important for our team, showing that we're headed in the right direction. And the first one happened in January of 2011, and it was the discovery of Kepler 10b. Kepler 10 is the name of the star, and then you put a little b next to it to denote a planet. If there are two planets, you put a little c. So the first discovery I'd like to tell you about is Kepler 10b. Kepler 10b was the discovery of our first rocky planet. Something outside the solar system, orbiting another star, a star very much like our own sun, that you can actually stand on, something that's actually rocky. Okay? And what you're seeing here is not an actual picture of the planet. It's an artist's depiction of what it might look like. And a lot of it is flight of fancy or imagination, but a lot of it is actually based on things that we know, that we see in the data, and I'll talk a little bit about that in a second. There are actually 2 planets associated with Kepler 10b, or with Kepler 10. Here's the star Kepler 10, here's Kepler 10b, this tiny little thing, and then some distance out is another planet, Kepler 10c, which is about 2.5 times the size of Earth, so it's bigger. But what I'd like to do is talk about Kepler 10b a little bit and use it as an example of what the data actually looks like. So you've seen lots of beautiful pictures from the Hubble Space Telescope. Here's what our science data looks like. Quite as exciting, okay, I admit it. It's just a bunch of white points. These white points tell us a lot. You remember the green cartoon, right? Well, this is the green cartoon, but now it's actual data, okay? Every white point is a brightness measurement, and it's plotted as a function of time. So let's see, what do we notice? Well, first we notice that there are some empty areas, right? Like this one. And those are places where actually the telescope stopped taking data for a little time. They were safe mode events, and I can tell you more about that if you're interested later. You also notice that there's kind of a lot of up and down and up and down and up and down. And a lot of that is just measurement uncertainty. We can't take a perfect measurement of the brightness. There's some error bar or uncertainty associated with it. But there's also a periodic set of dimmings. Do you guys see it? Do you see what looks like a transit event in the light curve? Where all of a sudden the brightness drops and does so repetitively?
Yes.
What do you think? 6 of them? He says there are 6 of them. See them? Take your best guess, and now I will show you. Maybe it'll be obvious once I show you. Here's a set of vertical lines that mark them. You see them? Right here, the brightness, this white point, dropped for a time, and then came back up, and kept on its way, and then dropped again. And then came back up. That happens when the planet passes in front of the star. That's the transit event. Okay? Now, that's not the transit of Kepler 10b. That's the transit of Kepler 10c. If you look at this light curve, you might also notice that there's all this up and down and up and down and up and down in here, but there's also kind of a set of points that are raining down from that systematically. Well, let's look at that more carefully. What I'll do is I'll zoom in on maybe just a tiny little region here. Let's zoom in on that and see what the brightness points are actually doing. And this is what it looks like. Here's that one deep event. So the brightness was going along, and then it dims because of Kepler 10c, and then it goes along again. But do you see another transit event in there? Can you convince yourself that it's there?
Something higher frequency.
Higher frequency?
What do you think? Is it believable? If not, I'm out of a job.
If not, she's not out of a job.
It's a very, very strong signal, actually. I don't have to do any fancy averaging or statistical analysis to be able to see it. Just we saw it in the first 10 days of data. Just step out of the solar. That's the signal of Kepler 10b. And it's not very much larger than the signal, what the signal of an Earth would be around the sun. This dim light is consistent with a planet that's only 1.4 times the size of our own. Okay, 40% larger. Okay, so the Kepler data tells us what the radius or the size of the planet is. How much dimming you get. What we really want to know also is the mass. Because if we have the mass and we have the radius, we can compute mass divided by volume, which is density. Yes. Density is mass divided by volume, right? Sure. And that will tell us something about composition. Then we'll know if this is something that's rocket we stand on, or if it's something gaseous like Jupiter, Saturn, Uranus, and Neptune that have a density like water on average. Okay, so how are we going to do this? We want the mass. I'm going to explain to you 2 different ways that we get mass. And the first one is illustrated by Kepler 10b. When you have a planet orbiting a star, the star is actually orbiting the planet too. We don't think of it that way. We think of the planets as doing all the motion, and the star in the center is stationary. But in fact, the planet and the star are both orbiting, and they're orbiting about the common center of mass. Imagine you put the star on one end of a rod and you put the planet on the other end of the rod. The planet's really tiny, the star's really big, and you want to put your finger on the rod to balance it, right? That's the center of mass. And where are you going to put your finger? You're going to put it very close to the star to balance it, right? Okay, that's the center of mass. And the two objects are going to orbit around that point. So the star is here, and the star is just going to orbit that point very tightly. But the planet is over here. And it's going to go around the same point, but it's going to have to move a lot. So we know this happens. We know that's how it works, because we understand gravity. And what we're going to try to do is take a measurement of the star to see if we can detect the motion as it goes back and forth in this tight orbit. Okay. So we go to our 10-meter telescope in Hawaii that collects a lot of light from the stars, and we take that light and we spread it out into a spectrum. Okay, just like a rainbow that you have through a crystal with sunshine coming through your window. We spread it out into a rainbow. But here's what a rainbow of a star looks like. Right? Red, orange, yellow, green, blue, top to bottom. And that's fine. That looks like a rainbow. But what you might notice is this rainbow has all these black blemishes on it. These are called absorption lines. These are places where the atmosphere of that star are eating away that specific color of light. And so they don't reach our telescope and they don't get collected and spread out into the rainbow. They're missing. Okay? And if a star is moving, we've got the Doppler effect, which says that the location, the color of those black missing light splotches, blemishes, is going to shift back and forth towards the blue if it's moving towards you, and then towards the red if it's moving away from you. And so I have an animation just to illustrate what we actually see. Let's focus in, let's zoom in on one of these absorption lines, and you have it spread out against the grid of the pixels of silicon that's measuring the light. And so you'll see that move back and forth against the pixels, and the light level that you measure in each of these pixels is going to change. So that's the Doppler effect, and this is a powerful way of getting the mass of the planet, if it's measurable, if that signal's big enough. For Kepler 10b, a planet that's only 1.4 times the radius of Earth, we were worried it's not going to be big enough. Our technology can measure a star velocity maybe as small as kind of a jogging speed. Okay, maybe 5 or 10 meters per second. Can you jog 5 or 10 meters per second? Right? And Kepler 10b's velocity is probably going to be smaller than that. So we weren't sure we would be able to see it. But this is what the data looked like. So here's a plot of all of these velocity measurements from the Doppler effect. We took about 40 some odd measurements of the star. And indeed, you saw quite clearly the velocity swing up to a positive number, then down to a negative number as the star goes first forward and then backward, forward and back. And the amplitude of that signal was only 3 meters per second. That's without walking speed. Okay? That's the speed of the star. That's what it meant. Okay, so this signal tells us that the mass of Kepler 10b is about 4.5 times the mass of the Earth. And the error bars that we had on that number were very small. Similarly, the error bars we had on the radius, 1.4, that's very small error bars. And so when we calculate the density, we get a number, 9 grams per cubic centimeter. And there's no theoretical model of a planet that you could build that isn't consistent with something that's rocky at that density. And that's how we know that Kepler 10b is absolutely a rocky planet. Okay. So this just shows you that you get the radius, the size from measuring the light curve, looking at the dimming. You get the mass from the Doppler effect from the 10-meter telescope, and And you put those together, and you get mass over volume equals density. Does anybody know the density of the Earth? About 5 grams per cubic centimeter. What about Jupiter and Saturn? About 1, which is the density of water.
1.
Okay. Well, I'm going to tell you now about another way that we can get mass that's become very, very powerful. And, oh, no, I'm not going to do that yet. What I'd like to do is share something with you. So you already saw the artist's depiction of Kepler 10b, right? And it looked like a planet very different from our own Earth, right? Now I'm going to show you this artist's depiction was done by a gentleman named Dana Barry. And Dana Barry actually got some money to do a National Geographic documentary, and he used this artwork in that documentary. So look for it. It's called Finding the Next Earth, and you'll see this similar footage in that documentary. So let me walk you through it. We start with a star very much like our own sun. Okay, this is a G-type star, but it's older. It's about 10 billion years old, not 4.5 billion years old like our own sun. So there she is. And coming in on the left-hand side is that tiny little speck of a rock that is Kepler 10b, shown to scale against the star. It's orbiting 23 times closer to its star than Mercury is to our sun. So the star-facing side is extremely hot. It orbits its star in less than 1 day. Because it's so hot, it probably doesn't have any atmosphere. However, some of these rocky particles might evaporate off the surface and then condense out into particles that you see being swept away from the planet, kind of like a comet, when a comet comes close into the sun, forming a little bit of a tail. So we're going to do a flyby now. We actually did some calculations to see if Kepler 10b could still be volcanically active or maybe have plate tectonics. It's pretty old, and planets get cooler as they age. But it's also more massive. So just like a big baked potato retains its heat for a long time compared to a small baked potato, Kepler 10b is probably still got a lot of energy inside of it and could still be volcanically active. So there's the star rising on the horizon. It's about 60 times larger in the sky than our own sun is on ours. And we've got an entire hemisphere of this planet, something the size of the Pacific Ocean, that is an ocean, but it's not an ocean of water we know is necessary for life. It's an ocean out of molten rock, right? Lava. An entire ocean of lava. Yeah, that's exciting. All right, so there she is, Kepler 10b, a rock suspended in the sun. All right, the next one I'd like to talk about is down here in the lower corner, Kepler 11. And what I haven't told you is that those 2,326 planet candidates that you saw in the beginning plot, those are actually associated with only 1,791 stars. What that means is that a lot of the stars that we're observing have multiple planet candidate signatures, just like Kepler 10b had 2, right? And so here's a cartoon with little orbital, we call these orreries, showing the planets and their separation from the star as their orbital little cross. And Kepler 11 is a system that had not 2 like Kepler 10b or Kepler 10, not 3 or 4 or even 5. Kepler 11 has 6 periodic dimmings of light associated with it. We had to disentangle all of them and then to understand the individual planets that are associated with Kepler 11. This is very different than our own solar system. 5 of these planets are actually closer to their star than Mercury is in our own solar system. So the things that are very nearby. One of them is between Mercury and Venus. We got the masses of 5 of these planets, but we did not do it with the Kepler 10-meter telescope in the way that I just described to you, with this Doppler effect, motion back and forth. We did it a little bit differently. And here's what happens. When you have planets that are very closely packed to one another, strange things happen to their orbits.